Hi, in this video we'll learn on how to test the hypothesis made about the two population means or to construct confidence interval estimate of the difference between the two population means. For this section we only focus on independent samples, and for the next section we'll focus on dependent samples. For independent samples, if the sample values from one population are not related or somehow naturally pair or match with the sample values from the other populations. And for the dependent samples or the matched pairs, if the sample values are somehow matched, where the matching is based on some inherent relationships. For example, when we talk about the weights of 8 M&Ms, the two samples are independent and are not matched. Why? Because picking a value from one color does not affect the choosing of the other color. So I have the 8 M&M balls, and if I just pick a random weight for the yellow color, it doesn't matter for the brown one. I just have to pick 8 of them for the yellows and then 8 of them for the brown. So they are completely independent. So picking one color, one weight for one color, doesn't affect the value of the brown or the other color. Now consider these dependent samples, the heights of the husband and wife. The two samples are the matched pair or dependent because once I pick the value of the husband height, then I must pick the husband wife to get the height, because we collect the data for the heights of the husband and the wife. So if I collect the first data for one husband, then the next data for the wife, it has to be his wife. I cannot just pick other person. So they are matched pair, or the value of one thing or the height of the husband will depend on the value of the wife. They have to go together because we consider the height of husband and wife. So the two data, they are together for the dependent samples. This is the process for constructing the hypothesis testings. Now there are two parts. The part one, we focus on independent samples with the standard deviation of the population 1 and the standard deviation of the population 2 unknowns, and we assume that they are not equal. Okay, so again we have two population 1 and 2. N1 is the sample size of the population 1, the same way for N2. Mu1 is the population mean. Sigma 1 is the population standard deviation. The x1 with the bar is the sample mean. The s1 is the sample standard deviation. The same thing applied to the second population or population 2. Before we can do any of the hypothesis testing, make sure we check the requirements. If we don't meet the requirements, then the value that you get at the end, it is not a true value, or the methods that you are using is not effective. Make sure that the standard deviation for the population 1 and 2, they are unknowns. We don't know the value of them. And make sure that they are different. So the population 1 standard deviation is different from the population 2 standard deviation. And then of course the two samples, they are independent. So picking one value from one sample, the first one doesn't affect the value of the second sample. They are not matched pair, they are not dependent, they are independent. And also make sure that they are simple random samples. And the last one is we require both of the sample size need to be at least 30. At least 30. If this requirement does not meet, then we require both the samples. They must come from the population having a normal distribution. And we can use the normal quantile plots to check for this requirement. Okay, if the sample size are below 30, then we have to check this requirement. Okay, as always, we have two different methods we use for the testing. Either we can use the p-value method or we can use the critical value method. I prefer the p-value methods because a lot of technology nowadays they display the p-value methods, especially the TI-83 or 84 plus. They have the program to display the p-value methods. Okay, so before we can do anything, make sure we determine the correct null and alternative hypothesis in one of the following three ways. Again, there are three cases: the two tails, the left tail, and the right tail. For all of the cases, the null hypothesis always involve the equality. That means we first assume that the mean, the sample mean, mu1 and mu2, sorry, this is the population mean. The sample mean is the x1 with the bar. So mu1 and mu2, we assume that the two populations, they have the same mean, okay, for the null hypothesis. So the null hypothesis always involves the equal sign. We assume that their mean are equal. Then if we claim that they are different, that means we talk about the case of two tails. If the mean of population 1 is less than the mean of population 2, this is the left tail, or is greater than for the right tail. Now, just a quick review, similar to the last few sections, if the arrow is pointing to the left, this is the left tail, okay? So mu1 is the population mean for population 1, and mu2 is for the second one. After we determine the null and alternative hypothesis, we select a level of significant alpha, and this will depend on the seriousness of making a type 1 error. Again, alpha is the probability of making a type 1 error, and the common choice is usually 0.05, but the problem will give you the level of alpha. And after that, we will compute the test statistics. It's just like the last section. We have to get the test statistic. For the mean, we will use the student t distribution. So that's why we will focus on the t statistics here. And the test statistic is computed using this formula. We take the sample mean, we subtract that, and minus the mu1 subtract mu2, and divide by the square root of s1 squared divided by n1 plus s2 squared divided by n2. S1 again, S1 is the sample 1 standard deviation, S2 is the sample 2 standard deviations. And after we get the test statistic, we can use the table A3 or technology to determine the p-value. And if we do use the technology TI-83 or 84, we use the commands tcdf. This is the cumulative area under the t curve to find the student t distribution, the area under the curve. And the commands will take three values: the lower bound, the upper bound, and the degree of freedom. Now, we have two samples, sample 1 and sample 2. To find the degree of freedom, we choose the smaller degree of freedom between the two samples. So the degree of freedom of sample 1 is n1 minus 1. The degree of freedom of sample 2 is n2 minus 1. Remember, it's just the sample size subtract 1. Now, to find the degree of freedom, we pick between the two of them, pick the smaller value. Okay, so for the two tails, this is the test statistic. So after we find the test statistic, we can locate the lower bound and the upper bounds to use in here. For the two tail case, all you do is you take the area under one tail and just double it to find the sum of the area in the tails. For the left tail, we only focus on the left area, and for the right tail, we focus on the right area only. And because again the student t distribution curve, this is symmetric, so all you have to do is just find one area, multiply by 2 to get to the other one. Okay, and if p-value is less than the alpha is the probability of making the type 1 error. So if p-value is less than alpha, we reject the null hypothesis. If p-value is greater than alpha, we do not reject the null hypothesis, or we fail to reject. So that is the p-value method. If you don't want the p-value method, we can also use the critical value method. Now, to use the critical value method, we repeat the same process as above for step 1 and 3, and we then use the table A3 to find the critical value instead of the p-value. So once you find the critical value, T alpha or T alpha over 2 for the two tails, then we can compare the critical value with the test statistic. If the test statistic is inside the critical region, then we reject the null hypothesis. If the test statistic is outside of the critical region, then we do not reject the null hypothesis. Okay, so let's now focus on this example to demonstrate what I just presented to you for the process of doing the hypothesis testing. The results of a state mathematics test for random samples of students taught by 2 different teachers at the same school are shown below in this table. Can you conclude that there is a difference? Okay, so the claim here is that they ask you to conclude that there is a difference. Different means we use a different sign instead of a less than or greater than sign. So different means this is a different sign. And different signs apply for the two tails, right? The two tail case right here. This is a different sign. Okay. So this question is saying that, can you conclude that there's a difference in the mean? This is the key word. So we are testing about the mean between 2 samples. Sample 1 is from teacher 1, sample 2, or sorry, the population 1 is the teacher 1, and the other population 2 is the teacher number 2 class. Okay, so can you conclude that there's a difference between the means for the test scores for the students between the 2 teachers? And in this case, we use the level of significant alpha equals 0.10 or 0.1, assuming that the population is normally distributed. So we assume the populations are normally distributed and the population variance are not equal. Okay. So again, in this case, we focus on the methods below here is only for the independent sample and sigma are unknown, the standard deviation are unknown, and assumed not to be equal. So the problem already give you the information that the variance, they are not equal, so we are good. Okay, so we assume that they are not equal, and the populations are normally distributed. Why do we need this value here? This info here, because if you consider here, this is the sample size is only 8 and 18. They are less than 30. They are less than 30. That means you have to check that the 2 populations are normally distributed. And yes, this statement right here gives you that info. Okay, so we are given the degree of freedom. We are given the sample mean for the teacher 1, sample mean for teacher 2. S1 is the sample standard deviation. S2 is also the sample standard deviation for the class from the teacher 2. Degree of freedom is a sample size subtract 1, and we pick the smaller one to find the TCDF. It's right here. Degree of freedom, we pick the smaller one. That's why I picked the degree of freedom should be 7. Okay, so we don't know the population standard deviation. They are unknown and they are not equal. So the first requirement is yes. They are independent sample, yes. They are same or random sample. Yes, because we randomly select them. And yes, this is okay, right? Because we know that the two sample size, sorry, the two sample data come from population having a normally distributed data. So yes. So okay, so after all the requirements are okay, we then use the t-test statistic. Now let's apply the p-value. Okay, so for the null hypothesis, we assume that the two population mean they are equal, and this is the claim. We are trying to see if they are different or not. So this is the claim, and of course this is the two-tailed test. And now we use the test statistic formula, okay, T0, and because we assume that they are equal, mu1 equal mu2 from the null hypothesis here, that means this term is gone because mu1 and mu2 they are equal. If they are equal, when you subtract them, it's gone. Now on the top we have x1 bar subtract x2 bar. We got the value from here, x1 bar, x2 bar. So just plug in s1. We are given from the problem s1, s2. So just square that, and then 1 and 2 we are also given right here in this chart. So we have everything. So just throw them in the formula, and then just find the value 0.922. Now we know that this is the two tails, so I graph the curve with the two area. This is the test statistic T0, 0.0922. This is the positive value, so I label that to the right area, and all I have to do now is I find one area, I multiply that by 2. Okay, so I use the TCDF function to find the area for the right hand side here. The lower bound is from this value 0.922. The upper bound we go all the way to the right, so I use 10 to the 99 for a very large value. And then the real freedom, I pick the smaller one between the two, which is 7 right here, 7. And then after that I find up the value and then multiply that by 2 to get 0.387. This is bigger than alpha. If this is bigger than alpha, the level of significance, we do not reject the null hypothesis. Okay, let's try the critical value and see if they are consistent or not. Now, to find the critical value methods, we have to find the critical values. So we are given alpha to be 0.10 because this is the two tails, so I have to find the alpha over 2, which is 0.025. So 0.25 area for the right tail and 0.25 the same area for the left tail. Now, to find the critical value, we have the area. We just want to find the critical value. All we do is we use the inverse t function. And the inverse t function takes the value of the area to the left of that area. Okay, so this is the t alpha over 2. I input inverse t, and then I take the area to the left of this value. So this is 0.05 area. So to find all the area to the left of that, we take 1, which is the whole thing, subtract 0.05 to the right. Then we get whatever to the left of that. And then we take the degree of freedom, which is the smaller one, which is 7. And then that gives me 1.895. This is the critical value. Now, our test statistic we found above here is 0.922. 0.922 is lower than 1.895. This is the critical value. And this is 1.8, so 0.9 should be somewhere on the left, smaller than that. 0 is in the middle, so it should be on the left side. And you know that the left side of that critical value means the test statistic is not inside the critical region. Therefore, if not inside, you do not reject the null hypothesis. And we do end up with the same conclusion. That means we do not reject the null hypothesis. If we do not reject the null hypothesis, meaning that there is not enough evidence at the 10% level of significance to support the claim that the mean mathematics test scores for the student of the two teachers are different. Because we do not reject this null hypothesis, that means we do not have enough evidence to conclude that H1 is true, or the mean score of the two classes are different. So we cannot conclude or support the alternative hypothesis because we did not reject the H0. Okay, now the next topic is we construct and interpret the confidence intervals, rewriting the difference of the two independent means. Now, if you want to find the confidence interval for the two independent means, we can apply this formula here. T alpha over 2 is the critical value, and we use the smaller degree of freedom between n1 minus 1 or n2 minus 1 to compute the critical values. Okay, let's using the same example, we now construct and interpret the same 90% confidence interval about the difference between the mean test scores of teacher 1 versus the mean mathematics scores of teacher 2 from the last example. Now, recall from the last example, we already checked all the requirements. We also found the critical value from the last example. So all you have to do is we find the lower bound and the upper bound using the formula we just saw here, right? So everything was given. So all you have to do is you plug in the value for x1 bar, x2 bar, t alpha over 2, s1 square, s2 square, everything we have here. So we got the lower bound to be minus 14.76 and the upper bound to be 42.76. So the confidence interval is this up to this one. So we are 90% confident that the difference between the mean mathematics scores of teacher 1 and teacher 2 is between this score and this score. Now, because the confidence interval does contain 0, because in order to go from negative to some positive value, you have to go to 0. So 0 is in between. So this confidence interval does contain 0. We then can conclude that the mean mathematics score between the teacher 1 and teacher 2, they are the same. Why? Because if we see that the null hypothesis is mu1 equal mu2, we assume that this is equal. So when you subtract mu2 on both sides, we get the right side to be 0, or the difference between them should be 0, and this confidence interval does contain a 0. Therefore, we conclude that this is true, because if this is true, you get 0, and we do have the 0 inside its confidence interval. Therefore, we can conclude that the two mean score they are the same from the confidence interval. Now, you can also use a TI-83 or 84 to check all the work that we just did above. So again, I use the same example, so nothing is changing, but now we don't have to do anything by hand. We just use the TI-83 or 84, and that should give you the consistent or the same answer. Okay, to test the claim using the p-values, we use the two-sample t-test. Because this is the student t distribution, so we use the two-sample t-test. The two-sample t-test, this is for independent samples to find a p-value. And this performs a t-significant test to compare the means of the two population 1 and 2. Okay? And make sure that this is only okay if all the requirements are good. If not, then you get some value that is completely wrong. Now to do that, we go ahead, we hit the start button, and we go to the right arrow. We hit the test. So turn on, hit the start, and then go to the test column, and then we choose the two-sample t-test, which is the option 4. Okay. So after you enter into that, we go to in this case, we are given the stats, so you don't have to compute all the data. We are not given the data. We are given the sample statistic. So you have to pick the stats for the option, and then just go ahead to enter x1 bar, s1, n1, x2 bar, and so on. So the reason we pick this because we are given the statistic, not the data. Okay. So if you are given the data instead of the statistic, then you have to enter into the input using the data mode. And again, you have to store all the data to the list 1 and list 2, and then just pick the correct alternative hypothesis. Okay, so we enter everything into here from the given data, and then the reason and we also pick the null hypothesis to be different, right? The H1 is different. Now we pick the pool to be null. Why? We only choose yes for pool if we assume the two sample standard deviation are equal. In this case, again, we assume that the two sample standard deviation, they are not equal. The samples, the standard deviation of the two population, they are not equal, and that's why we pick the option no. Pick yes only if they are equal, if the two sample standard deviation are equal, and in this case they are not equal. S1 is 39, S2 is 24, so they are not equal. Okay, and then just hit the calculate button, and that should give you the test statistic, which is the T 0.922. That was the value we got earlier, 0.922, which is right here, 0.922. The same thing, right? That's the test statistic, 0.922. The p-value we got earlier was 0.387. Okay, let's go down here to see what's the TI give you. The p-value is 0.379. Okay, this is a little bit off comparing to the last example. It's not a big difference, but they are not the same thing. Why? Okay, why are they not the same in this case for the p-value? Well, the p-values we got earlier was 0. This is 0.379, and before we got 0.387. So a little bit different. Not a big deal, but why they are different? They are different here because of the degree of freedom. Okay. The reason the p-value is slightly different from our hand calculated value, because the graphing calculator TI-83 or 84, they use a more accurate formula to estimate for the degree of freedom. The degree of freedom is calculated by this complicated formula. Remember, for our hand calculation, we only pick the smaller degree of freedom between the two samples. We do not use this complicated formula. But the TI-83 or 84, they use a more accurate formula. That's why they give a little bit different from what we obtained earlier for the p-value. Okay, but picking a smaller value of the two sample for the degree of freedom is good enough. The difference is not huge. It's okay. Now to test a claim using the p-value, so we can also constructing a 90% confidence interval about the difference between the means and to find the confidence interval as earlier. So I use the two sample T, INT stands for interval, to construct the confidence interval. Again, we have two samples, so make sure you two sample T. This is the T statistic, T interval. Now to do that, we hit the start button and then go to test, and then go all the way down to option 0, two sample T interval, hit enter, and then again use the start and then enter all the data from the chart. And again, the pool is for no because the two sample standard deviation are not the same. The confidence interval is 90%. Why? Yeah, because the problem asks you to construct a 90%. 90% in decimal is 0.9, C level, confidence level, and then hit the calculate, and you should end up with the same consistent answer. So minus 13.67 and 41.669, and that should be similar to what we got here. Again, a little bit off, a little bit different due to the degree of freedom that the program, they use a more accurate formula or complicated formula. Okay, and yeah, the reason between the two values is because they just use a more complicated formula for the degree of freedom that we discussed earlier. Okay, so that is how you use the TI-83 or 84 to construct the confidence interval for the two independent sample means, and also use that to find a p-value. Again, so a lot of the technology, including the TI-83 or 84, they display the p-value. That's why the p-value is popular, because you can check that from the technology. Okay, so that is the end of this section, and for the next section we will learn about the dependent sample. And thanks for watching.